Novel Methods for Improving Accuracy of ASR Systems. This section concentrates on two novel approaches adopted in ASR systems for agglutinative languages. In the first approach, an enhanced bigram or trigram morpheme-based language model is designed to reduce the vocabulary size and reliably predict the strings in an agglutinative language. The second approach leverages the syllabic structure of the word and builds a syllable-based acoustic model. A language model is defined as the probability distribution over strings in a language. Frequencies of patterns of words as they occur in any training corpus are recorded as probability distributions. A language model is an indispensable part of ASR and machine translation systems. Language model helps in reducing the decoder's search space and in generating optimal sequence of words. For strict word order languages like English, statistical language models have been effectively used because trigram or bigram models accurately model short-distance relationship in a sentence. Other sophisticated language models also exist like class-based model, distance-based model and dependency-based model. The performance of a statistical language model is measured in terms of perplexity. The perplexity refers to the branching factor in the search graph. If the perplexity is low, better the performance of a language model. Owing to resource deficiency in text and annotated corpora in Tamil, building reliable statistical language models is a difficult task. Even with the available corpus, the agglutinative nature of the language further deepens the problem. Statistical studies using large corpora are still in the nascent stage. However, Rajendran, 2006, has given a review of various recent works carried out in morphological analysis, morphological disambiguation, shallow parsing, pause tagging and syntactic parsing in Tamil. For instance, let Y1 and Y be two consecutive words in a text. The probability Y vertical bar Y1 is the bigram that measures the correlation between the words Y1 and Y. This bigram measure is sufficient for modeling strings of words in a language where inflectional morphology is low. However, in agglutinative languages, like Tamil, a more minute measure is warranted. This issue has been successfully resolved by Saraswati and Geeta, 2007, with their enhanced morpheme-based language model. The size of the vocabulary was reduced by decomposing the words into stems and endings. These subword units, morphemes, are stored in the vocabulary separately. The enhanced morpheme-based language model is designed and trained on the decomposed corpus. A Tamil text corpus is decomposed into stem and its associated suffixes using an existing Tamil morphological analyzer, Anandan P. et al., 2002. The decomposition helps reduce the number of distinct words by around 40% on two different corpora, namely news and politics. The stems and its endings are marked with a special character hash for stems and $ for suffixes in order to code join them back after recognition is done. A general morpheme-based language model is one where the stem and suffixes are treated as independent words. No distinction is made between a stem and a morpheme. Depicts the various probability measures involved in a morpheme-based language model. The word Y1 is split into the stem C1 and suffix A1, and the word Y is split into the stem C and suffix A. In this case, the prediction of suffix A1 will be based on C1, which is strongly correlated since a stem can have a few suffixes among the possible 7 suffixes. This information is modeled in PA1 vertical bar C1 and PA vertical bar C, which can be reliably gathered from a corpus. However, the correlation between stem C and the suffix of the previous word A1 is weak, because the suffix bears very little information of the next word in a sentence. But when it comes to stem correlation, the probability PC vertical bar C1 can be reliably used, since there is contextual information that exists between adjacent words in a sentence and stem is the primary part of a word. In Tamil language there is strong subject-predicate agreement which leads to contextual information between suffixes of words in a sentence. This information is available in PA vertical bar A1. The perplexity and var are obtained using a Tamil speech recognition system. While Figure 3.A portrays the perplexity of the language models, Figure 3.B compares the var of the ASR system employing both language models. The results has confirmed that the modified morpheme-based trigram language model with Cat's back-off smoothing technique is better perplexity and lower var on two Tamil corpora. The results confirm that the proposed enhanced morpheme-based language model is much better than the word-based language models for agglutinative languages. Morpheme-based language modeling. The importance of syllable as a unit in ASR was felt in early researches starting with Fujimura 1975, where irregularities in phonemes have been discussed and it has been claimed that a syllable will serve as the viable minimal unit of speech in time domain. In the paper, Greenberg 1998, it is stated that pronunciation variation in switchboard corpus is more systematic at the level of a syllable. It has been emphasized that the onset and nucleus of a syllable do not show much contextual dependencies while the coda may still be susceptible to some contextual effects with the following syllable. Greenberg, 1998, proposed that syllables are frequently realized in their standard or canonical form, but in the case of phones, canonical realization is mostly unusual. In the paper by Ganapathyaraju et al., 2001, the first successful robust LVCSR system that used syllable-level acoustic unit in telephone bandwidth spontaneous speech is reported. The paper begins with a conjecture that syllable-based system would perform better than existing triphone systems and concludes with experimental verification after comparing a syllable-based system performance with that of a word internal and a crossword triphone system on publicly available databases, viz. Switchboard and Alpha Digits. A number of syllable-based experiments involving syllables in C phones, syllables in CD phones, syllables, monosyllabic words in CD phones have been reported in that paper. However, this system is deficient especially in the integration of syllable and phone models as mixed word entry. It is because mixing models of different lengths and context might result only in marginal improvements. Thangarajan et al., 2008a, have proposed a syllable-based language model for combating the agglutinative nature of Tamil language. The basic syllable consonant vowel phonotactics in Tamil is characterized by a regular expression shown in equation 3. There are constraints on which consonants can appear in each of the three consonant positions and in combination with vowels. With no constraints, the maximum number of syllables will be 183 times 12 equals 69,984. However, because of constraints, the actual number of possible syllables is an order of magnitude smaller. The number of lexically attested syllable is smaller still. In addition, there are constraints on stress patterning in Tamil words. Properties that constitute prosody are fundamental frequency or formant F0, perceived pitch, duration, intensity, perceived loudness, and to some extent vowel quality. Prosodic properties of speech are also used in detection of word boundaries and in other higher tasks of speech understanding like encoding or decoding pragmatic differences like a statement versus a question, emotion and so on. At the word level, prosodic properties encode lexical tone, lexical stress and lexical pitch accent. There are two types of prosodic syllables, namely Ner Asai and Nirai Asai. Ner Asai is monosyllabic. It may consist of either one short vowel or one long vowel, either of which may be open or closed, i.e. ending in a vowel or consonants respectively. Nirai Asai is always disyllabic with an obligatorily short vowel at first position, while the second phoneme is unrestricted. Like Ner Asai, Nirai Asai may also be of open or closed type. The prosodic syllable representation can take any of the following 8 patterns as shown in Table 3. An uninflected Tamil word may comprise 1 to 4 prosodic syllables. The linguistic rules of Tamil prosodic syllables. Prosodic syllables are composed of phonemes. Based on the linguistic rules tabulated in Table 3, a regular expression can be formulated as shown in Equation 4. This expression describes all the possible patterns of prosodic syllables. In other words, an optional short vowel is followed obligatorily by either a short vowel or a long vowel, and 0 or 1 or 2 consonants. Theoretically, the number of prosodic syllables will be quite larger, of the order of 3,674,160, since there are 90, 18 times 5, short vowels, 126, 18 times 7, long vowels and 18 consonants. But, the actual number will be smaller due to constraints like phonotactics and morphotactics. Hence, it is essential to estimate the number of prosodic syllables with the help of a corpus. In this section, a Tamil text corpus provided by Central Institute for Indian Languages, CIL, with 2.6 million words is taken and useful statistics about prosodic syllables is collected. This corpus is a collection of Tamil text documents collected from various domains, viz. Agriculture, biographies, cooking tips and news articles.